record. Let me write down chapter 15, number 55. Let's me set up my video camera here. Get some paper to write with. Okay. So you guys can kind of see my doodle pad. Let me share my camera with you. Oh, we got to connect it. Okay. Chapter 15, number 55. I'll write on the screen here. And then I better put page 1. You know, like yesterday, I still got it sitting over there. We did like 7 pages for one problem. That was crazy. It looks like my camera's angled funny. Oh, can't get it to stay, but maybe that'll be a little better. Okay. Okay. Nice. All right, so let me jump over here to, let's see, 123 homework. Aha, okay. And all right, so let me begin this one, number 55. Oh, okay, good. And like yesterday, I think some of you were here yesterday. Let me point out that, you know, this chapter 15 is a continuation of where chapters 1 through 14 left off. So don't be surprised if many times I look back and I say, hey, remember Newton's second law? Hey, remember conservation of energy? You know, all those things that you learned. And on this one here, we have a pendulum, and a pendulum pivots. So this is really Newton's second law using rotation.
Right. I actually got an answer, and I looked at the solution, the provided solution. I used Newton's second law for translation, and I got an answer that was it looked almost the same, minus like a couple tweaks, and I was trying to make my answer look like the solutions. And I was just wondering if I did something minor wrong, or if mine was correct, just, you know, looked a little bit different. So I just wanted to see you go through it. But yeah, I did use translation and not
yeah, the translation is going to be off a little bit.
Yeah.
And that's what happened. That's what, you can't do a translational problem like this because the forces are at different positions, which results in different torque. You got to have position, you got to have torque.
Okay.
All right. So I think you'll see the difference as we move along here. So let me draw the picture. Here's kind of the ceiling. Here is the pendulum that's got this mass, and it's a concentrated mass. And so if that's all you had, in other words, a pivoting problem, a rotational problem can reduce down to a translational problem if you don't have the mass distributed like a moment of inertia, and if you don't have forces at different locations. And what I mean by that is the force of gravity is acting on the mass, but the force from the spring is acting at a position that they call H. So you don't have forces at the same location, so they end up in being different torques, and that's why translation won't work.
Right. So there's no way to solve this using translation, or are you saying it would just be pretty hard?
There's no way. It doesn't. It doesn't fit the I hate to say easy category because there really is no easy problems at this level,
Right.
but translational motion is easier than rotational motion.
Right.
And yeah, one of the things that you're probably still learning, but first exposed to in 121 is that when do you recognize a problem has to be a rotational problem versus a translational problem?
Right.
And so I'm starting off by saying, since it pivots, that tells me right away it's a rotational problem. However, if the forces were at the same location and the mass wasn't spread out, then rotational problems turn into, or can be done with translational problems, but we don't have that.
So you're saying if the extension of the pendulum was like a rod with mass, then you would be able to use translation? Is that what you're saying?
I guess I'm saying if, I'll do it a different color. If this spring was pushing at the same point that gravity is pushing, because the gravity is pushing where the mass is.
Oh, so okay, I see. Yeah, it's because the forces are acting at different locations.
Yeah.
Okay, yeah, that makes sense.
Yeah, and you'll see it when we work out the numbers here, how when you do the torque, the lever arm is going to be L for gravity, but it's going to be H for the spring.
Right.
And if they were the same, then the L on both sides of the equation would cancel off and your torque would reduce down to just force. And now the translational.
Makes sense.
Yeah. And I'll just say, if you had something like this, if you had something pivoting that was, the mass was distributed, so it's a rod, there's no way you can do this with translational.
Because then moment of inertia comes in.
Yeah, and the moment of inertia comes in because the force of gravity on this little chunk is here, but on this chunk is here, and on this chunk is here. So again, you have force of gravity pulling at different locations. They have different lever arms, and so you can't make it a translational problem. If you try, you will get close, but slightly off, and I think that's what you've discovered.
Yeah.
Okay, so yeah, great theoretical discussion here. That the first step is really going back to 121 and recognizing that this must be done with Newton's second law of rotation, can't be done with Newton's second law of translation. So I'll just put some of the forces equaling MA and put a big X in it and say, no. That's just not going to work. Not going to be able to solve that problem this way. All right. So now I will recognize that, okay, now I need to do my torques. So the first torque, I will say, comes from the spring. And again, maybe I'll just kind of review here. Physics, again, 121. Where the torque is this cross product between the lever arm and the force, which in terms of magnitude would be the R, the F, and the sine of the angle between them. So if you come over here, and you look at, I'll put torque from the spring, the distance, the lever arm is a distance h. The force is coming from the spring, so that's minus kx. Now, here's where I want to be a little careful. X is what? Well, X is how much the spring gets either stretched or compressed. And so if you can imagine this weight going back and forth, this right here, this spring would be compressed a little bit, X. And then the other direction, it would be stretched a little bit, distance, X. And so that's what that X represents, okay? The angle is this angle here. Now, as you can see, as it rocks back and forth, that angle does change a little bit. And this is where I'm going to read into the problem a little bit. If you'll notice, especially since you're this far in the homework, number 55, you've seen us do the pendulums and we make some rough approximation.
Right. Yeah.
So for this one, I would say that the angle is 90 degrees when it's right at the middle.
Mhm.
When it swings a little bit, it goes a hair under 90. When it goes over here, it goes a hair above 90. But it's approximately 90. Maybe
Right.
it's 88. So I'm going to put maybe kind of, I don't know, I'll put a range, maybe 85 to 90. But if you get out your calculator and you do the sine of 85, it's pretty close to 1.
Yeah.
Sine of 90 is pretty close, is exactly 1.
And it does, in the problem, it does say for small theta, which makes me think they want us to use that small angle approximation.
Good, because yes, and that's it. Good. Good. Okay, so anyway, so what I'm going to do here is just call that a 1. Okay. Now I'm going to move the negative in front. I'm going to put the K in front of that. I'm going to put an H. Now watch what I do with this X. Now the X, as it swings back and forth here, is the kind of the length of the arc. Now, not where the mass is swinging, but where the spring is connected. And so I'm going to go back to, again, probably something you saw a lot in your 121, that the arc length S is equal to the radius times the angle that it moves. Now, I want to be careful and point out that the angle I'm talking about now is this angle. See, a moment ago, I was talking about this angle, the angle between R and F. But now I'm talking about this angle that's swinging here, okay? And that's a small angle, okay? But nonetheless, when I look at this problem and I come back up to this equation from our 121, or actually, I guess this is really from geometry, arc length, this S is this arc length X. So I'm going to replace it with the radius, which would be an H, and the angle. So if I simplify that, and I'll put a circle around it, that is the amount of torque I get from the spring.
So when you went from X to H theta, that was that only because it's a small angle, or is that like, because isn't the arc length that the pendulum swings different than the extension of the spring in general?
Yeah, so, okay, so if I were to draw a vertical line and take the arc would look like this, the spring would probably compress along a linear line.
So it's because the angle is small that we can say that X is the arc length.
Yes.
Basically. Okay.
Yeah. So that's where that key is important, that, hey, we're talking about small angles.
Okay.
And of course, my general rule is small angles, anything under 30 degrees, because the sine of, well, what's 30 degrees in radians? Pi over 6?
Yeah, pi over 6.
So the sine of pi over 6 is about 5% off of pi over 6. So if you're willing to accept a 5% error, you can go up to 30 degrees. And that's kind of what we call a 95% confident rate.
Right. Okay.
All right. So, and 30 degrees is a pretty good swing. So
Yeah.
you know, I would argue that, we say small angles, but it's very, very reasonable for the way most things would oscillate. You wouldn't want like something on a bridge oscillating or swinging more than 30 degrees. Okay, so I've done the first torque, right? The torque from the spring. Right, let me go on to page 2 here. Okay, so page 2. Let's look at the torque from the force of gravity. So I'll just draw the pendulum without the spring for a moment, put the mass here, and say, all right, the force of gravity is mg, but the object is constrained. Maybe put a grid on here to move on the x-axis. Now, again, same thing. The x-axis isn't really the arc length, but again, for small angles, they are. Okay, so same thing as we just said. All right. So if I look at this and I see how much of the force of gravity is kind of angling down there, okay, what we call the restoring. I might do something. I should have drawn a better grid. Let me do this. Let me redraw that. So I'm going to draw the force of gravity down, mg. But what I'd like to draw, and I didn't do a good job here, my apologies, is draw the x-axis to where, this is where the pendulum would be tied up here, to where it, wants to go back, because this force of gravity, mg, can be thought of as this much. I call this angle theta. This would be mg cosine theta. So this would be the component of the force that would be like tugging on the string. Mm-hmm. And this over here would be the mg sine theta. So again, maybe this is a good physics 121 review where I'm saying, okay, take the force of gravity and break it into its components. This is the part pushing it back. In fact, this is the same thing we did in 121 of something on a hillside. If it was on an incline and you said, well, how much is pushing it down the incline? We said it's mg sine of theta. Okay. And so this theta in this diagram is actually the same theta that the pendulum swings. So again, coming back to page 1, I just want to be real clear about what angle we're talking about, because when we did the spring, the first time we talked about the angle between the spring and the pendulum, and that was near 90 degrees. But the second angle was the angle of the swing. And that's what I'm talking here. This theta is the angle of the swing. And mathematically, if I use the equation for the small angle approximation, I can call it mg sine theta. Okay. So now let me write here. Let me change back to this pen. Let me write the torque from gravity. I'll put a G here. And just to review our torque, it's R, F, and sine of the angle between R and F. So the R is the distance away. So in this case, it would be L. So there's L. The force, well, that's what we just did. I didn't put a minus sign up here, but I think you can see back here, it's in the negative direction. Let me make sure I put it here now. Mg sine theta. Okay. And then
Wouldn't that already take care of the sine theta and the torque equation, because that
thank
would
you.
that
Yeah,
would make it perpendicular to the
yeah. Okay. And then of course, then doing it this way, this component would be perpendicular. So technically it'd be sine of 90
Yeah.
degrees. But
yeah
yeah,
yeah.
thank you. Thank you. And there's I kind of mixed the two approaches there for a second. All right. So sine of 90. So good. I'm glad you noticed that. So I'll cross that out. So now I'll just put the minus in front. I will put the M first for whatever reason, then the L, then the G, then the sine theta, and I'll circle it and say, okay, that's the torque I get from the force of gravity. All right. So now I can put this all together. Because remember, if we go back to page 1, our goal here was to say add up all the torques and set it equal to I alpha. Okay, so we've done the two torques. The first torque was from the spring. So let me put a minus kh squared theta. And now let me do the one from page 2. This is the force of gravity. So this is minus mlg theta. And that's supposed to equal to I alpha. Now let me simplify things a little bit. I'll start by pulling out a negative and also pulling out a theta. So this would be kh squared plus mlg. Then we got the moment of inertia. And again, I guess we have to go back to physics 121 for that. You remember the moment of inertia is you add up the mass and the position of all the pieces that make up the object. I think this is chapter 10, if I remember right.
Mm-hmm.
Okay, now our object's pretty simple. I think they're saying just take all the mass at the end of the string. In other words, don't worry about the mass of the string. So I only have one object to add together.
Wouldn't it just be well, ml squared? I guess I was going to say mr squared, but yeah, ml squared.
Yeah. So the r would be L in this case, and so that's the. So I mean, some of these moment of inertia can be hard, and fortunately, that was an easy one.
Yeah.
And then the alpha is actually the second derivative of theta, and that theta is the swing angle, which I should say that's the swing angle. So all right. So now we are in a position that if anybody out there listening didn't catch it, we're always looking in this chapter for something that looks like this. You have a negative, you have some kind of function. It could be x, it could be theta. But if that equals to the second derivative of that same function, then this out in front, I'll call it box, means omega is the square root of box. And so all of the work that we do in this class, if it ever comes down to this equation, then it is simple harmonic motion.
And then we can get everything they ask.
Right. And then we have everything. And so that's what I actually have here, right? Now, maybe I need to move the M and the L squared to the other side. So it looks like I have this type of formula where I have the second derivative of it. I've got the negative, I've got the function. And so that up there must be the omega. So omega must be the square root of kh squared plus mlg over ml squared, which the period is 2 pi over the omega. So you let me take that omega and flip it. I get ml squared over kh squared plus mlg. And let me go back to the question. What are we looking for?
Pretty sure it's just the frequency.
So the frequency, which is the reciprocal of the period, would then be 1 over 2 pi, and then k h squared plus mlg over ml squared. And I think I answered it, hopefully correctly. Let me see what the solution guide says.
Yeah, I'm pretty sure that was in the solution.
Okay.
Yeah, when I did it with translation, I got something similar, but it was not quite right.
Yeah, you'll be a little off. Let's see, 1 over 2 pi MDL. Yep. Yeah, because again, when you do translation, there's no way to distinguish between the H and the L.
Right.
And so if I replace the H with an L, I would get what I would get with just translational motion.
Right. Okay, cool. Thank you.
Nice. All right, good hard one for me. All right, so there's our first real good one here for today. David, I'll give you another shot here if you.
Oh, I'm here. Where did you? I stepped out of the room for just a second, but I'm here.
Okay.
Wait, did you say Dana or David?
I said David.
Oh,
Dana?
okay, never mind.
This is just a quick one about the homework.
Dana, I don't throw your question in the chat so I don't accidentally pass you up.
Oh, I did. I put it in the chat, but I put it directly to you instead of to everyone. That probably is why you don't see it.
Oh, and you know
it's
what?
like a paragraph. It was like a paragraph of a question.
Okay, but also I try to use 2 computers here.
Oh.
And so it must be on my host computer one.
Yeah, it is. It is.
Yeah. So let me call it up the chat on the host. Yeah, I see. Perfect, Dana.
Okay.
Let's see.
I'm not in a hurry, so whatever order.
Okay, so David's actually ahead of you. So I'll go to David, but I'm going to write down yours because you're next, and you say you would like to do 21 and 24. Okay, I'm gonna write that down. 21 and 24, so I don't have to kind of come back to this. I see. I like my laptop, but it's so small. I can't see you guys or what I'm doing really well, and so I just like to use it for the camera. Because my desktop doesn't have a camera, so.
I'll put it in the other one next time.
Yeah. So yeah. So okay. So technically, David, you're next here. You had another question.
Just real simple. It's one of the conceptual. Is Dana's question from 102 or 123?
She's from 123, and they might be kind of long.
Okay.
Those are big
Yeah.
ones.
Okay. Yeah. Just on the benefits and the disadvantages of the metric system compared to standard. The only thing I think advantages of the standard is just converting the units and the metric.
Oh yeah, I'm not a big. I'm not a big.
I didn't think so either. I'm just trying to. Is there anything else besides the conversion issues?
You know what? No, because the conversion is. Well, I guess I'd say there's 2 things. The conversion being base 10 means you can convert pretty easy in your head. That's the big. Because if somebody asked me, how many feet were in 1.3 miles, I would go, ooh, I need a calculator for that. But I'm basically just multiplying by 5,280 feet. Where if they asked me how many meters were in 1.3 kilometers, it's the same thing. I would just multiply by 1,000. And that I could do in my head real easily.
Yeah.
So that's the real advantage of the metric system, that it's a base 10. But the other nice advantage of the metric system is they don't play word games. In other words, the prefixes give it away. In other words, if I said, how long was a centimeter, and I had never heard of centimeter, I get the idea that there's 100 centimeters because a centa means 100. And if somebody were to, say how long is a kilometer, and I had never heard of a kilometer before, I could go, well, that's easy. It's 1,000 meters because kilo means a 1,000. So the naming of the units is also a big advantage. But other than that, you're just multiplying by some factor.
Yeah. And so the only disadvantage of the metric is having to converting to standard in the only nation that hasn't adopted it, our country. But if you run across it,
yeah. And
that's
that's
just
all right.
Overthinking it.
All right. Let's see. Side by side. Let me change my view here. So I got you guys side by side. All right. So now let me go to data here. All right. So what time is it? I'm going to put a little note here. 12:04. And Dana will do 21 first. I might as well do it in numerical order.
Awesome. And I have, I was able to look at the solution and get the answer. But my problem was understanding what they were saying. Like when it says, what is it? The part is during the first cycle for T equals whatever, at what value of T is the system's potential energy changing most rapidly to kinetic energy? I just was so confused. At what point, what now? And I couldn't, my brain is just not understanding, how would I take, I read this chapter 2 or 3 times, and I watched the lecture 4 times and took really good notes. And I still how do I read that and understand what they're asking?
Forgive me for chuckling, but you got a great question. And I think everybody's question has it. And I'll put it in a broader content is the hardest part of word problems is the translation of what are they asking in words. So how do I do that in math? Okay. And if it makes you feel any better, I think most students struggle with the wording on this one. Also, if it makes you feel any better, the wording on this one really has I don't want to say it. It's the wording is not really related to this chapter. So no matter how carefully you read this chapter, no matter how carefully you took the notes, the wording is actually mathematical. And so it goes back to your math class, if that makes you feel any better.
And I was struggling in my last 2 math classes. So that could be why it was so hard. I was reading it and I was like, I don't understand what language are you speaking.
So I think maybe the best way I could help you is to maybe go through my thinking. What would I be thinking as I read this? Okay.
Yeah.
So let me just read it out loud here. I would say this. It says, a card is attached to a spring, okay, with a constant of 3.24 newtons per meter and vibrates such that its position is given by this function. Okay. So far, I would say everything I've read has to do with this chapter. I would say, okay, I've got this little spring. It's hooked to some mass. It's going to be then moving back and forth. And they gave me this equation. So let me just write it down. That has an amplitude of 5. And it's in centimeters. And then it has a cosine. And then they give me this 3.6 T. Okay. Now, I like to encourage students to, not only do the math, but kind of make sure you read the math, understand the math. Sometimes that helps me by making a picture. So my next step would be to say, well, what does a cosine function look like? Well, it starts at its maximum, so that must be 5. And then it oscillates. Okay. Now, I know I haven't really got to the crutch of your question yet. Please forgive me. I'm just kind of thinking out loud, going, okay, this is kind of what I would do first.
Yes.
Okay. I might also be curious of what this meant physically. So let's see, this would really mean that it starts at its maximum. So that means it gets pulled over the 5 and then lets go. And so it starts at its maximum and goes back and forth, back and forth. Okay. Okay. I guess I would also be curious maybe to know, well, I wonder how long it would take to go from its maximum here to the other side and then back again. In other words, if this graph is a time axis, how much time is one cycle? And we call that the period. And the period is 2 pi over omega. Now, omega is that number in front of the t variable in the trig function. So 2 pi over 3.6. And so maybe I would just take my calculator and go 2 times pi divided by 3.6, and I get about a 1.75 seconds. Okay, so it does one cycle every 1.7 seconds. Now watch what happens when I continue to read. It says during the first cycle for time 0 to 1.75 seconds. See, now that makes more sense to me. I'm glad I did this calculation because they're saying that during this cycle, during that first cycle, 1.75, of course, then everything repeats again. All right, so they're really just saying during that first cycle, I got it. Okay, so they even use that phrase. During that first cycle, from 0 to 1.75 seconds, at what value of time is the system's, here it is. Here's that weird wording. The system's potential energy changing most rapidly into kinetic energy. So I read that and I go, it's changing the most rapid. Okay.
Does that mean like when it's changing direction or when it's in the center of?
No. Okay. So let me maybe plot what would the potential energy of a spring look like if I made a graph. So we're talking here that the potential energy of a spring is 1/2 kx squared. Now, if I put in my x here, and let me go ahead and put it in meters, but this is what I wanted you to see, a cosine squared. So, okay, I was making a plot of potential energy versus time, and I'm only going to do one cycle. So I'm only going to go to 1.75. What does this mean? So here's the position. Here is a cosine squared. And so a cosine squared function starts here and goes to 0. When the spring gets compressed, again, since it's x squared, it gets to be positive energy. Then it gets to 0 again. And then it gets positive. And maybe I should have just put it a cosine squared function in green over here. That's what a cosine squared is. Okay. All right. So they are asking, and again, I'm taking my time here because this is just weird wording, and that's what you're struggling with here. It says, what value in time is the energy changing the most rapidly? Oh, so that sounds like a math problem. Math, when does a function change the most? When the slope is the most. So that would be here, or here, or here, or here. Now, do they say changing into kinetic energy or changing into potential energy? Let me go back and read. As the system's potential energy changes most rapidly into kinetic energy. Okay, so when the potential energy is decreasing, that is when it's going into kinetic energy. So I'm going to put a box around. This is the one they would want. This one right here has a big slope, but the potential energy is increasing. So we are gaining potential energy and losing kinetic energy. So that has a nice big slope, but it's not the one that they asked for. And then this one here would be the same as that one. Put a box around. This is when it is changing the most rapidly. That is, it is decreasing the most. It is changing the most rapidly into kinetic energy. Then, of course, this is the place where the potential energy is increasing. So therefore, the kinetic energy is decreasing. So that's not the one they would want there. And so I guess I'm saying I kind of answered this with a combination of math and physics 121. That's the part I was saying here, that you could be very careful reading this problem in this chapter, but those particular words were not from this chapter or this semester. So, don't feel like you missed anything in the reading.
That was very helpful. What my brain wasn't connecting was as the potential energy decreases, the kinetic energy increases. Like I couldn't remember the relationship between the two or something. And that's the picture I needed to see. Now it makes more sense.
Yeah, and so that was, that's the conservation of energy, the chapter 8 from physics 121. Yes, that's a big thing. And one thing I think we'll discover, and I'll say this to everybody because I think everybody begins to discover it, is you go through physics 121 and you kind of feel like you got it, or you go through calculus and you kind of feel like you got it, and you did, and maybe you even got a really good grade, maybe you got an A. But then the next class asks you to really begin to use it. And I think that's where you almost learn the class before it a little bit better, if not even better than you did while you were in that class. Because you keep falling back on it going, oh, yeah. And the pieces actually start coming together. I know for me, I think I learned pre-calculus best when I took calculus because I was struggling with the calculus and I began to learn it wasn't the calculus I was struggling with. It was all these logarithms and exponentials that we were using in our calculus, but we weren't talking about them. And anyways,
yeah,
this is kind of that same thing that, nowhere in here did I teach you conservation of energy, but you got to use it to make sense out of it.
Yeah. Thank you.
Okay. And do you want me to go on to try to solve this, or are you good? Or
no, I'm good. That was the part that was the part that I was struggling with, was the conceptualization of it. Like, how do I got the answer and I could follow along with what they did, but I was just like, how am I going to read a question on a test and be like, oh, this is what I do? Like my brain just wasn't. Yeah. So I think that's all. And even, let me see number 24.
And I know this, I would not feel comfortable writing an exam question with those kind of wording. That was just
Phew.
that could be better worded. I'm not saying it's bad, and it would be bad if it was on an exam. It would maybe not so bad on a homework problem where you have time to digest what's going on.
Okay.
So nice. Okay, and then so your other one was number 24. And so let me put a time here. Let's see, 12, 19, number 24. And let's see, what does 24 say? Let's see if I can get my piece of paper lined up. 24 says the seconds pendulum is one that moves through its equilibrium position once each second. That is, the period is 2 seconds. Yeah, now let me just pause right there because again, those words can get a little confusing because a cycle for a pendulum would be one complete cycle. That is, if we started the pendulum on its left, then it would swing all the way over to its right and then back to its left. Did you notice it went through the equilibrium twice for one cycle? Or maybe if we started it on the right, it would swing down, go to the left, and come back. So again, it went through the equilibrium twice. That's one cycle. If we started it right at the bottom here, which I guess we could do that by maybe coming along and tapping it. A full cycle means it goes to the right, back to equilibrium. That's not a cycle yet. Goes over to the left and comes back. So a full cycle goes through this equilibrium twice. So if they, and I'm glad the author uses a quote here. He says, a seconds pendulum is one that moves through its equilibrium position each second. So what it's saying is if you tapped it, it would take 1 second to go up to the right and then back. That's 1 second. It would take another second to go to the left and then back again. So the period is a full 2 seconds. And so that's why it's called a seconds pendulum. Every time it goes to equilibrium, it's 1 second. Now, here it says the length of the second pendulum, and so L equals 0.9927 meters. In Tokyo, Japan. It's interesting. Not sure where this question's going. Okay, so we got in Tokyo. And it's a little different, 0.9942 meters in Cambridge, England. Okay. What is the ratio of the free fall? Okay, so in class and in the book and in lecture, we derive the period of a pendulum. Now, we did a small angle approximation. So sticking to small angles, we said the period is 2 pi times the square root of L over G, where G is the acceleration due to gravity. And what this pendulum is saying here is that G varies slightly from place to place on the globe. And if it's different in Tokyo and Cambridge, that means you must have a slightly different L to correspond to a period of exactly 2 seconds. And we can then use this pendulum as a way to figure out what the value of G is in these different locations.
I see. I did not understand the question.
Okay,
Okay.
that's
Okay.
totally cool. Yeah, yeah. So yes, you and for everybody else, it's, half of doing these physics problems is really that I call it the translational step, the step where you have to go and say, hey, what is this question really asking? Hey, now this is interesting. I see my video froze of me in the Zoom, but
But your audio is still okay. I mean,
my audio is good, and it looks like my screen share is good. Let me jump
yeah.
back. My other one, is it? Yeah. Okay. Well, I'll keep going unless something worse happens. And just for completeness, it sounds like you're ready to move on, but I'll just go ahead and then just finish the math here. If I put like
Yeah.
well, they're both equal to 2 seconds. So if I say 2 pi times the square root of the length, and I'll put a little sub t for Tokyo, over G in Tokyo, then must be equal to 2 pi times the square root of the length in Cambridge to the G in Cambridge. And then, of course, 2 pi's can cancel off. We could even square them. And it looks like the ratio of the G's would come out to be the same as the ratios of the L's. And so maybe I'll write it Cambridge to Tokyo as the length of Cambridge to Tokyo. And Cambridge was 0.9942. Tokyo was 0.9927. So it looks All right. Hello, am I back on here? Can anybody hear me?
I can hear you.
Yeah, we can hear you.
Okay. Good. All of a sudden, my laptop just like crapped out and died. That was weird. Well, it had already frozen my video. So, yeah, but you guys can hear me?
We can hear you.
Okay. Let me try to share again. And see if that still works. I see my laptop giving me a video camera error. So I don't think I could get my picture in. But it looks like everything else is okay. All right. Can you guys see my screen share?
Yep.
Okay, good. All right. And then I'll keep going. I just won't have a video of me. I wonder why I did that. Anyways, Nicholas, I was asking you if that made sense, and I don't know if you tried to answer that while I was gone or that helped.
I'm sorry, what?
Did I answer your question? Because if you replied, I didn't hear anything.
I don't think I heard your response.
Oh,
Actually.
okay, okay. All right. So for your question was about the chapters.
Yeah.
Okay. Do we want to turn in, or it says, do you want us to turn in your homework whenever we complete a chapter or two, or are we supposed to turn it in on the 17th? The choice is yours. I'm giving you up to the 17th to work out any bugs. That's really the reason why. And so you could hang on to it and, use it to study, but it's officially not due until the test day. That just kind of helps people get started, especially people who add late, and maybe people who, have never done the PDF conversion anyway. So for a lot of reasons, I just put the first due date as the test date and give us some time to figure it out. And actually, by that time, you will have turned in 3 labs, so people will figure it out by then.
Okay, so like let's say next week when we finish our chapter 2 homework, we're not supposed to turn it in, then we can wait until the due date, correct?
Yeah.
Okay, cool, perfect.
Yeah, I would encourage you just kind of keep them in a notebook, and you're going to turn them all in on the day of the exam.
Yep, got it. Thank you.
Okay. All right. Maria, I think he said to turn in you're answering the question. I have to go, Professor. Yes, and thank you for helping me answer it, although sounds like you're gone now. Okay, enjoy. James, will the exams for 123 be administered online or in person this semester? Oh, well, let's see. James, I'm trying to look at the enrollment here. I think you're signed up for the in-person one, because obviously the people who signed up for online, they're going to take it online. You, for in-person, I'll say that you're going to take it in person. However, the first test is scheduled before we go back. So the first test, the first exam, which is only a half exam, is going to have to be online for sure. And I think what I'll go ahead and do, because it's so weird the way we're starting, and I'm really not even sure, what's going to happen with this pandemic, but I know that so many of you will be blocked from campus because maybe you have a cold, not coronavirus, but you'll fail the admission test and you have to stay home for like 10 days. So all of you in-person people, I guess I'll just, give you the option of being online for everything. So if you want to take the test online, you can. If you want to watch the video lecture online, you want to mix it up, you want to come in for the test, or you want to come in for the lecture, but take the test online, whichever you'd like, James. Your choice.
I guess that goes for 102 as well, correct?
Yeah, for 102 as well.
Okay,
The first exam is going to have to be online because it comes before our return date. But even
Yeah.
after that, I feel like I've got to have that option out there because when it comes to test day, both classes have like 75 people in them. So, oh no, the in-persons are a little smaller than that. But anyways, the in-person ones, still, there's going to be somebody who's going to be prohibited from coming on campus for like 10 days. And then anyway, so I'll just have to keep that option open that you guys can do anything online or in person, whichever you want to or need to do.
okay.
Yeah, and hopefully I won't get the flu or something, let alone coronavirus. But if I get the flu, I can't come on campus, so we'll have to be online. Yeah. All right. James, I don't see you on here, but I hope that helped. I'll send you an email too. The Jasfire. Okay, I guess that wasn't a question, just chatting along. Okay, Nicholas, you say, oh, okay. Thank you for hosting office hours. Okay, you are welcome. Going down, Nicholas again. What happened? No idea. Seems like the issue on his end. Yeah, I have no audio. Yeah, me neither. And then me. Yeah, sorry, my laptop tried out, logging back in, and I think I'm back. Yeah, real sorry about that. And I got to figure out what happened to this camera, but I'll do that after 2 o'clock, after this time together is finished, or if we finish early, who knows. All right, hey everybody. Well, I got to the end of the chats, I believe. I don't see any more questions in the chat. You guys have anything you want to ask? Just verbally or throw in the chat. Will, let's see. Will says, I did the questions on the PDF for chapter 1. Okay, good. And I was wondering if that is all I have to do for homework on chapter 1. Yes. Now, and I hope you saw this, Will. For chapter 1, they're in 2 sections. There is a first section which says conceptual questions, and right below that are exercises. So make sure you do both the conceptual and the exercises for chapter 1. Then you'll see a line. Okay, yes, I did. Okay, good. And then you'll see a line, and that is the start of chapter 2. So you don't need to do chapter 2 yet. That's what I will assign to you for next week. So next week you'll be starting on doing the homework for chapter 2. All right, you are welcome, Nicholas. Oh, good. Glad I answered that, Will.
I guess I got a quick little question.
Yeah, go ahead.
So it's on the homework again for 123.
Uh-huh.
So it's number 49. I did the problem and you sent out a solution. I don't know if it was from the semester or previous one, but I watched it and I got it. I just kind of wanted to have a discussion about, I guess I was just confused on, so it's the one where 2 blocks or there's a smaller block on a bigger block and they're oscillating. And I guess I was just confused on the step where the friction force, I don't even know how to put this in words. So like the friction force is causing the acceleration of the second block, which is the same acceleration as the whole system or something. I just was a little confused on the step where you go from, I guess on my paper, I have like the static friction is less than coefficient and the normal force, but the friction also equals MA. And then I don't know, I just have some discrepancy with some of the steps.
Okay. So let me, again, like a lot of these problems, I think every problem, there is the new stuff we're doing, but also a big piece of this is the mechanics that we learned back in 121 here. Okay.
Mm-hmm.
So if I was doing a free body diagram of the top block, the force of gravity is pulling it down, mg. Now let me read the question. Do they label the top one as an M1 or an M2 or block A? Let's see.
They go B and P. So the top block they call block B for boy. B as in boy.
Okay, so I'll put a sub B down here. So M sub BG is pulling down on the top block. That's gravity. Pushing up on the top block is the normal force, which of course comes from the bottom block, which is a P. Okay. But then what makes it move, and this is the main part of the problem, what makes it move back and forth is friction. And if we want the top block to be moving with the bottom block, then the friction would be static friction. Okay.
Mm-hmm.
Okay. So let's review static friction. Static friction is an inequality. So static friction can be a small value up to a maximum value.
Right.
So this block then, and I'll say here then, maximum, I'll put a little maximum static friction would be normal times the coefficient of static friction. You might say that would have to equal mass of block B times the maximum acceleration. So if the acceleration ever got to be greater than whatever this calculates out, then you wouldn't have enough friction to give it acceleration. And so what would happen is the lower block would slide away from the top block. You just don't have enough push.
So that's essentially that step that you just did was applying Newton's second law for just the top block.
Yeah, good point. So this was
the X direction, right?
Sum of the forces in the X direction equals mass times acceleration.
I think where I got confused was I tried to apply Newton's second law to both blocks at the same time. And yeah, got a little lost there.
And you know, and I should point out there, you know, there is times, and it can be useful to think about both blocks together or them separately. In this particular case, I'm not sure we want to think of them together ever, but maybe the maximum amplitude of oscillation.
I think I was just thinking that because the question says what what maximum amplitude of oscillation can the system have? So I was just thinking about them as a system.
Yeah, good point. Yeah, good point. Yeah, and I think we would have to view them as a system for a moment. In my little doodles so far, I have not thought of them as a system yet.
I guess that would eliminate, though, the force of friction, because that would be an internal force, correct? If you view them as a single system.
Yeah, but also to view it as a single system, you would have to also make sure they're not sliding, because I think when you're viewing them as a single system, you are saying both objects have the same acceleration. And if they start sliding on each other, then that's no longer true.
Right. Okay.
So the potential, so as long as they're not, as long as it's not sliding, there's nothing wrong with viewing them as a whole system here. In fact, you got me curious. Maybe I'm going to keep going here. If I were to put mu s and then put in the normal force, which would be mass of block B times G, and then mass of block B, and then this would be the maximum acceleration. The mass of block B drops off, and then this gives us a number, because I think if I read this, I haven't read the whole thing, but it says large block P executed harmonic, simple, executed horizontal, simple harmonic motion as it slides across a frictionless surface with a frequency of 1.5 hertz. Block B rests on it as shown in the figure, and the coefficient of static friction is 0.6. What is the maximum amplitude that the oscillation of the system can have? Yeah, and I see your point. You read the word system, and you jumped on that first. Nothing wrong with that. For some reason, I jumped on top block first and the amount of friction. Well, probably because of how you asked me. But if I would have read the whole question, I probably would have done the whole system first, like you did.
It does make sense, though, to think about just the top block, because that's really what, like, if there was no top block, then it would be fine. But the problem is if the top block slides, like the bottom block doesn't have a problem.
Yeah, so I'm thinking to do this problem, we have to do both. We have to think about it separately as its own free body diagram for the top block, like I just did. But then also, then we could think of it as a system, because we know that the maximum acceleration is omega squared times its amplitude. And we want to make sure
that's the system, right? Or like both of them together? Or
okay. Yeah. Okay. So yeah, now I'm shifting my thinking and thinking of them as a system.
Okay.
Because I might think of it this way. I might say that, okay, if I gave it a small amplitude, it would go back and forth, and this A would be small enough that it would be under this maximum amplitude of an oscillating system. And I guess a system has its most acceleration on the endpoints.
Mm-hmm.
So it would have this much acceleration at its endpoints. But if it had a number that was less than 5.88, then it would never slide. So in other words, if omega squared A was always less than 5.88, they would stay together. Which means that you want the amplitude to be less than 5.88 over omega squared. Now they don't give us omega, they give us the frequency, but omega is 2 pi times the frequency. So A needs to be less than 5.88 over 2 pi f squared. And so if I go 2 times pi times f, which was 1.5, I believe, yeah.
Mhm.
And square that, so that's the denominator. So 5.88 divided by that number, we're talking about a needs to be less than 0.0662. And I guess I should watch my units here. I did this in meters per second squared. So that means this comes out in meters. So as long as the amplitude is less than 6.62 centimeters, we would always have an acceleration of the system less than 5.88. And therefore, we will always have enough friction to keep up with the needed acceleration, and they would stay together.
Okay, yeah, that makes more sense. Thank you.
Nice one.
Hey.
Yeah.
I'm so confused right now because I wasn't here at first because I had
Okay.
class. So
No problem. Go ahead, Johnny.
so first when I go to your class in physics, I'm in physics 102.
Okay.
When I go there, there's no actually questions. There's like the first one, it says I have to turn it in by February 6th. But there's I don't see any file or something like that.
Oh, all right. Okay. So you're on Canvas, right?
Yeah.
Okay. So go to Canvas
Mhm.
and click on announcements.
Announcement. Okay.
Okay. And then I'm just going to look on announcements. There's a bunch of announcements I've been sending you.
There's 3 of them.
Okay. And one of them, I'm going to look it up. I think it's the first announcement, says welcome. And there it says the title is called Week 1 Assignments. Can you click on that one?
Yeah.
Okay. Now, read that. And it's kind of long.
I think I read it before, but
Okay.
a long time ago. It's like when you send it.
Oh, okay. But there's a little more to it. So yeah. So the first part talks about what I sent to you before class started.
Mm-hmm.
And it has the textbook and the lab manual and the homework pack and the syllabus. But keep going down because a little below that, it says, and it's kind of bold, it says, here is your first week's assignment.
Are they before the videos or after?
It's before the video because the videos are part of that section.
Oh, here, yeah.
All right, so then it says step 1, log into Canvas and make sure you can see everything. So you've done that one already.
Yeah.
So then it says step 2, read chapter 1 in the textbook.
Yeah, but where can I find that?
Okay, so the textbook, scroll up. That's the email that you said you saw. So
Yeah.
if you go, see the PDF that says Kirkpatrick?
There's four of them, right?
Yeah, there's 4 of
Yeah,
them up
yeah.
there.
The second one.
The second one, right? The first one's the syllabus. The second one is the textbook.
Okay.
Yeah, I probably should have made that clear that that is the textbook.
Oh, okay.
Yeah. So, and
Okay.
it's a pretty big PDF, so you probably want to download that
Okay.
and read that chapter.
Okay.
Now, after you read that chapter, then you're going to go to step 3, and that's where you saw those videos. So that's me lecturing on chapter 1.
Oh, okay.
Actually, the first 2 are kind of an introduction to the class. So watch those first 2, and those first 2, I'll be talking about, things like this. I'll say, hey, here's how we're going to do things online. We're going to, give you an assignment each Sunday night, blah, blah, blah. And so
Mhm.
make sure you watch the part that says intro to class part 1 and intro to class part 2.
Okay. Yeah.
And then chapter 1 actually starts. And so there's 3 parts to it. There's chapter 1, part 2, part
Yeah.
3.
Okay.
And then by the time you do all of that, then you're ready to actually then start the homework on step 4. Yeah.
Oh, okay. And where can I find the homework?
So okay, and then so go back up to where the textbook was, those 4.
Yeah.
So the first one is the syllabus, the second one is the textbook, the third one is the lab manual. You won't need that till next week.
Okay.
And then there's the 4th one. That's the homework assignment
Oh, okay. Oh,
when it says Physics 102 homework.
oh, okay, okay.
Yeah.
Oh, okay, that makes sense. Oh, okay, okay. So I have to do the homework, but until I have until February 17, right?
Yeah, now I'm not, since it takes a while for people kind of figure this out, kind of like you're doing now. I've given you a lot of time to do the homework, but don't put it off because we're going to do a chapter every week. So by the time February 17th comes, you'll have 6 homeworks due.
Oh, okay.
So you should do one every week.
Yeah, yeah, yeah.
And then and if you can't quite get it done, that's okay. But that's why I'm zooming here on, I guess, Tuesday, Thursdays, and Fridays, so that you guys can ask.
Oh, okay.
And
So yeah. So because I have class, I usually have class right now.
oh, okay.
I can't. Is it the Zoom required or like I have to be in here?
Yeah, no, the Zoom's not required. So it's just if you have a question.
Oh, okay. Is there any time if I need any question or something like that?
Yeah, there. If you go back to these announcements,
The announcement. Yeah.
and you'll see that there's the second announcement is links for my office hours on Tuesdays and Thursdays.
Oh,
And then also today, the third link is for today on Friday.
oh, okay. Okay. So,
So if you come to any of those, great. But also feel free anytime to shoot me an email. I'm pretty fast on my email. So I'll get back to you within a couple hours.
okay, sounds good.
And yeah. So
Okay, good.
don't hesitate to ask. Don't wait till the next Zoom session. If you have a question on Sunday night, send it Sunday night. Don't wait till Tuesday.
Okay, sounds good.
Okay.
Okay, thank you very much.
All right. Nice. Good. Good. All right. Let's see. Anything back into the chat? Nothing in the chat here. Let's see. Looks like, oh, good. Like I must be answering the majority of questions. We're getting down to just a few of you. Got 2 of you left here. Jasper or Trinit? Lost Trinit. Jasper, are you there? Do we have any questions, or shall we call it a wrap for today and keep working on this? Restart the recording here. Okay.
There's a little picture too, which is
57. Oh, okay. I see that one.
I guess. So when I first started the problem, I was, doing Newton's law for rotation and doing torques and everything. I guess I assumed from the beginning that the natural length of the spring was when the plank was horizontal and the angle was 0.
Oh, it doesn't matter, but yeah, that's good.
Well, I guess I was doing my torque analysis when the plank was pulled up at an angle, but then when I checked my solution, because my answer looked a little bit wrong, it looked like they had like an X naught and an X. I don't know. I was just a little confused on that. So If they had two values for or two variables for the x in the spring equation.
Yeah. So they probably did. Okay, so they probably did something like this. Well, let me read it. It says a horizontal plank of mass m, length L, is pivoting about one end. Okay, the plank's other end is supported by a spring with a force constant of K. All right. The moment of inertia of the plank is 1/3 ml squared. The plank is displaced by a small angle theta from it. And then there's a give it away horizontal equilibrium position and then released.
So that's like before the plank is pulled, when the angle is 0, that is when the spring is at its natural length, quote unquote.
Okay. Yeah. Okay. I'm sorry. I think you said it right. I'm not completely sure I understood what you said. Let me draw you this little picture here, because I think this is what's driving you batty. Is the spring has a natural length that I'm going to make it so that it's a little bit taller than the plank is, so that it actually in the spring in its natural length would make it angle up a little bit. Okay. But if you look carefully at those words, let's see, how did it say? It said a small angle theta from its horizontal equilibrium position. So what they mean is because the plank has some weight to it, so its center of mass is its middle. When you put it on this spring, what's going to happen is the weight of the plank is going to compress the spring a little bit. And so the spring is not really at its natural length at equilibrium.
Yeah, that's definitely what was messing with me. I first was thinking that like the plank started in that second picture and then someone or a force pulls it up and then lets it go and then it oscillates.
Okay, yeah. So if you just lowered the weight of the beam or plank on it, it would actually compress it a little bit.
Okay, yeah, that makes a little more sense. Yeah.
And so then if you were to maybe pull it up or push it down, which way do they do? It won't matter, but they might say, show that the plank moves in simple harmonic motion with this angular frequency. Okay.
Kind of a similar process to the last problem, right? You just, find the torques and then set up Newton's second law.
Right. And then there's a little interesting twist on this one, unlike the last one. I mean, well, the last one had its own interesting twist, but this twist is a little different because watch this for a second here. Let's just say then I slightly push it down a little bit. Okay.
Mm-hmm.
Okay. So when I go to add up the torques, and like we talked about last time, this would be a torque problem. And it has to be done as a torque because, number one, the mass is distributed. But what that really means is the effective force of gravity is at the center of the plank, but the force from the spring is at the end of the plank, and they're not at the same location. And there's no way to do this with translations. So I would give then the torque from gravity, okay, would be the distance. So that's half the length of the plank. So that would be L over 2 times the weight of the plank, mg, times the sine of the angle. And if you'll let us, like on the last time, do a, roughly a small angle approximation, that's roughly sine of 90 degrees. And the torque is a negative torque. It's pulling it in a clockwise direction. Okay. So there's the torque that I get from gravity. Now, let me add to it the torque I get from the spring. And if I understood, this is where your question was. So let's see, the torque would be the distance away, so that's L, times the force from the spring. So this would be negative K. And here's where I think you were asking the X. Let me say that the X is always labeled from the natural length of the spring. But I'm going to break that into two pieces. See, there is this first part that compressed the spring due to the weight of it. Then there's an additional more amount that I'm going to push down. So let me call that X naught plus X, where X naught is that first distance that compressed the spring. The X then is the additional amount from horizontal. So keep that in mind. This X is the distance from horizontal. This X is the amount that, compressed it to horizontal because of the weight of the plank. Does that make sense?
Yes. I think I'm still confused on, maybe I'm overthinking it, but like, where are we measuring, like, where is the equilibrium position, for the spring?
Okay, so, right. And let me be real clear about two different points, the natural length and the equilibrium length. Okay, so the natural length of the spring sticks up to here, where if you rested the plank on it, the plank would not be horizontal.
Or, okay, so would that also be if there was like no plank and there was just a spring, the spring would extend up to where you drew it in the first picture?
Right.
Okay.
So when I go to calculate the force from a spring, which we usually call Hooke's law, minus Kx, we measure X from its natural length. So this right here would be X equaling 0.
Okay.
So when I put the weight of the plank on it, which compresses it a little bit, that then is this first bit of force from the spring, the X naught. Then I push it a little bit more. Maybe I should call it X prime so you don't confuse it with this X, because this X up here is the total X that the spring has been compressed. And I'm saying it's made of two pieces. The total distance that the spring is compressed is this first part, X naught, which is what brings it down into equilibrium. Then this initial X prime is actually measured from this equilibrium point, not from the natural length. This is the additional amount I push it down.
So the X naught, does that, I'm trying to formulate this. So if the spring is just, if there's no plank and it's just the spring, it extends out to a certain length. And then when you when you rest the spring without pushing it down, that you're saying that compresses it, because the value of X naught?
Yeah.
And then you push it down even more.
Yes, to get it oscillating.
Okay.
So I'm going to break the compression of the spring into two pieces. This piece is from the weight of the plank,
Okay.
and this piece is my extra little push that I give it to disturb it and make it oscillate.
Okay.
Okay. And then I guess I would also say technically there would probably be the sine of 90 degrees for the torque, because the torque is the angle between the plank and the spring, which is roughly 90 degrees. So that's kind of boring for this problem.
Mhm.
Again, that equals to I alpha. So I would say technically I have three terms here. Because the first torque right here is from gravity. The second torque I've kind of made into two pieces. And you might still be wondering, why did I break it into two pieces? And here's why. Remember that we said this X naught is the amount that gets compressed because of the weight.
Is this kind of like when you went in the lecture, you went through the derivation of a vertical spring? Yeah.
Yep,
Yep.
it's exactly the same.
Okay. So the first term is just simply the weight of the plank, but then the spring constant, or not the spring constant, the spring force, initially before you push it, it's I'm still, so it's zero because, but isn't the spring force pulling it down also?
No, the spring's pushing it up. It's compressing it. I know it looks like it because it has a negative, but remember where the X is negative. So you've got a negative with a negative, you're compressing.
Right. Okay. Okay. Oh yeah, because so the force is always opposite displacement. So if the spring gets displaced down, then the force would be up. Okay.
Yeah.
Okay. Okay. So
So-
yeah, that makes sense that why there's zero now.
I
Okay.
actually, and I'm glad you said this is the same as the vertical spring, because what happened for the vertical spring also happens here. And that is, you can, once the oscillation starts, you can ignore the effect of gravity because it's been balanced by a small compression of the spring. And so you could treat this as if you were in outer space with no gravity, except this X is not measured from the natural length of the spring, it's measured from the equilibrium of the spring. So that's what gravity does. Gravity on the vertical spring, when you put the weight on a vertical spring and pull it down a little bit, and then let it go into oscillation, it does the same as if there was no gravity, except the equilibrium is lower down on the spring. It is not as if it was in outer space where the spring would have never been brought into an equilibrium position. It would have oscillated around the natural length of the spring. So the natural length of the spring and the equilibrium would be the same thing in outer space, but they're slightly different when you have gravity in them. So again, these two terms cancel off. And so this thing is going to oscillate, as I said, around its equilibrium position as if there was no gravity. Now, if there truly was no gravity, it would oscillate around the natural length of the spring. There would never be that initial compression. So there is a difference between gravity and no gravity.
Mm-hmm.
But that difference really is where the equilibrium position is. It doesn't change the frequency or anything because the compression of the spring carries the weight of gravity and cancels it off right here.
Okay. Yeah, that makes a lot more sense. And
Yeah,
then the
so
rest
now-
is- yeah.
If I keep going, now we're like we did on the other problems where x prime, this distance here from the equilibrium, is using the arc length is equal to radius times theta. The radius would be the length of this plank, so that would be an L, and then theta. The moment of inertia, fortunately, they give us, because I'm not sure how many would remember a plank is 1/3 ml squared when it's on its endpoint, but we can go back to chapter 10 and look that up. And then the angular acceleration is the angle, that it pivots. And so those two thetas are the same. So what I'm going to get is a negative with a theta. Looks like one of the L's will cancel out. But in the numerator, I will have that K, that L, and that 3. And in the denominator, I will have the mass. And now we're back to what we said earlier, that if you ever see an equation where you have a second derivative of a function and you get negative of that function back, that thing out in front is the angular frequency, or it's the square root.
I think the L actually is, there's 2 L's on both sides, isn't there?
Oh, thank you. Thank you. Yeah, there, I messed that up. There's 2 of them
Also,
on
the
both.
problem
Yeah.
says, it says show that the period is, or show that the frequency, angular frequency is the square root of 3K over M. So it gives you the answer,
Yeah.
before you solve it. So yeah, I looked at that and I was like, oh, there's no L in there.
Sorry. Yeah, there were 2 here. I don't know why I didn't see it. I don't know what I was thinking. But anyways, yeah. So those 2 on the left cancel with those 2 on the right, and you just have a 3K over an M. So there it is.
Cool.
Yep.
Yeah, that little discussion about the compression definitely helped. Appreciate that.
Yeah. Yeah, because without it, this really can get hard without it, because if you don't do that, then you have like this constant term from the torque of gravity, and it doesn't fit this equation that it's a function of angle.
Yeah, that's what I had. I had one term with a theta. I don't even remember how I got the theta. And then the other term was gravity without a theta. And I was like, how am I going to get that in the form? But
right.
Yep.
Right.
All right. Thank you.
Well, you bet.
Have a good one.
All right. Have a good one. You too.